Have you ever looked at a rainbow and felt that quiet sense of wonder, and then moved on without asking how something so breathtaking could be so precise? We were taught that rainbows are just sunlight and rain. A simple explanation, neat and complete. But what if I told you that almost everything you learned about rainbows is only the surface? What if the colours stretching across the sky are actually the result of a hidden geometric code? A perfectly calculated dance between light, water, and your own eyes. Today we're not just going to admire a rainbow, we're going to decode it. You'll discover why a rainbow doesn't actually exist in one place, why no two people ever see the same one, why a mysterious 42-degree angle governs its shape, and how the sky is quietly performing advanced physics every time it rains. By the end of this journey, you won't just see rainbows differently, you'll see reality differently. Because a rainbow is not just a beautiful accident of nature. It is proof that the universe hides extraordinary precision inside ordinary moments. Stay with me until the end, and I promise you this. The next time sunlight breaks through rain, you won't just look up in wonder. You'll look up with understanding. When most people think of a rainbow, they imagine it as a colourful arc sitting in the sky, almost like a physical object stretched between clouds. In reality, a rainbow is not an object located at a specific point in space. It is an optical event, a phenomenon created by the interaction of sunlight, water droplets, and the observer's eye. The colours you see are produced when sunlight enters tiny, spherical raindrops, bends due to refraction, reflects internally off the back of the droplet, and then bends again as it exits. This process separates white sunlight into its component wavelengths, creating the familiar spectrum of colours. However, the crucial detail often overlooked is that the light reaching your eyes comes only from droplets, positioned at a very specific angle relative to you and the sun. For the primary rainbow, this angle is about 42 degrees from the direction opposite the sun. Only droplets located along this precise geometric cone send the concentrated, colour-separated light toward your eyes. Droplets outside this angle do not contribute to the rainbow you perceive. Because this alignment depends entirely on your position, the rainbow has no fixed location you can approach or touch. As you move, the set of droplets sending light to you changes, and the rainbow shifts accordingly. What appears to be a stable arc in the sky is actually a dynamic, observer-dependent pattern of light, continuously reconstructed by physics at every moment you look at it. It may seem natural to assume that when two people stand side by side, looking at a rainbow, they are sharing the exact same visual experience. In reality, each observer is seeing a rainbow formed by a different set of water droplets. A rainbow appears when sunlight interacts with countless suspended droplets, but only those positioned at a precise angle relative to an individual observer's eyes contribute to what that person sees. For the primary rainbow, this angle is approximately 42 degrees from the direction opposite the sun. Light that reaches your eyes at that angle has undergone refraction upon entering the droplet, internal reflection at the back surface, and refraction again as it exits, separating into distinct colours. Because this geometry depends on the straight line connecting the sun, the droplet, and the observer, even a slight change in position alters which droplets satisfy the required angle. The droplets sending red, orange, yellow, green, blue, indigo, and violet light into your eyes are not the same droplets sending light into someone else's eyes, standing just a metre away. Each person's rainbow is centred on their own anti-solar point, creating a unique cone of refracted and reflected light. The visual arc appears similar from nearby viewpoints, but physically it is constructed from entirely different paths of light. The rainbow is therefore not a shared object in space, but a personal optical projection generated by precise geometric relationships between sunlight, water droplets, and the individual observer's perspective. The formation of a primary rainbow is governed by a precise geometric relationship often called the 42-degree secret. When sunlight enters a spherical water droplet, it slows down and bends due to refraction, because light travels more slowly in water than in air. The light then reflects off the inner back surface of the droplet and bends again as it exits back into the air. During this process, different wavelengths of light separate because they refract by slightly different amounts. However, the intensity of the emerging light is not uniform in all directions. Instead, it becomes concentrated around a specific angle relative to the incoming sunlight. For the primary rainbow, this angle is approximately 42 degrees, measured between the direction opposite the sun and the outgoing red light. Violet light, which bends more strongly, emerges at a slightly smaller angle of about 40 degrees. This difference in angles creates the spread of colours that form the arc. The reason 42 degrees appears so consistently is rooted in the mathematics of refraction and reflection inside spherical droplets. When physicists analyze the paths of millions of light rays passing through a droplet, they find that many rays cluster near this angle, producing a bright, concentrated band of color. Droplets positioned at other angles send light elsewhere, but only those aligned along this 42-degree cone relative to the observer contribute to the visible rainbow pattern in the sky. The reason red appears on the outer edge of a primary rainbow, while violet curves along the inner edge, is rooted in the fundamental property of light known as dispersion. Sunlight may appear white, but it is actually a mixture of many wavelengths, each corresponding to a different color. When this light enters a raindrop, it slows down because water has a higher refractive index than air. The slowing causes the light to bend, and the amount of bending depends on the wavelength. Longer wavelengths, such as red light, experience slightly less refraction, while shorter wavelengths, such as violet light, bend more strongly. As the light travels inside the droplet, it reflects off the inner back surface and then exits, bending again as it returns to the air. The two refractions combined with the internal reflection spread the colors apart. Because violet bends more both on entering and exiting the droplet, it emerges at a smaller angle relative to the incoming sunlight. Red, bending less, exits at a larger angle. For the primary rainbow, red light reaches the observer's eye at roughly 42 degrees from the antisolar direction, while violet reaches at about 40 degrees. This small angular difference is enough to separate the colors into a visible spectrum. The consistent ordering is not random or artistic. It is determined by the physics of how electromagnetic waves interact with water molecules, producing a structured, predictable gradient of color across the arc. A secondary rainbow forms when the path of sunlight inside a water droplet becomes more complex than in the primary case. Instead of reflecting once off the inner back surface of the droplet, the light reflects twice before exiting. This additional internal reflection changes both the angle at which the light emerges and the arrangement of the colors. Each reflection slightly reduces the intensity of the light because some energy escapes the droplet at every interaction. As a result, the secondary rainbow appears fainter and less vivid than the primary arc. The extra reflection also alters the geometry of the emerging rays. In the primary rainbow, red light exits at a larger angle than violet, placing red on the outer edge and violet on the inner edge. In the secondary rainbow, the second internal reflection effectively reverses this ordering. Violet now exits at a larger angle than red, causing the color sequence to flip. The secondary rainbow typically forms at an angle of about 50 to 53 degrees from the antisolar direction, which places it outside the primary rainbow. Between the two arcs, there is often a noticeably darker region known as Alexander's band, created because fewer light rays emerge at angles between the primary and secondary concentration zones. The presence of a double rainbow reveals how small changes in the path of light within microscopic droplets can produce entirely new, large-scale patterns in the sky, governed precisely by reflection, refraction, and geometric optics. What we usually see from the ground is only a partial view of a much larger geometric structure. A rainbow is not truly an arc. It is a full circle of light centered around the antisolar point, which lies directly opposite the sun from the observer's perspective. The reason we rarely see the complete circle is not because it does not exist, but because the horizon blocks the lower half. The ground physically prevents us from viewing the droplets that would send light upward into our eyes at the required angles below the horizon line. When an observer gains elevation, such as standing on a high mountain or flying in an airplane, the geometry changes. With the horizon lowered relative to the observer's field of view, droplets below eye level can now contribute to the optical pattern. In these conditions, the full circular form of the rainbow can become visible, surrounding the antisolar point like a luminous halo. The same 42-degree cone of light that forms the primary rainbow still governs the phenomenon, but now the complete cone intersects with visible droplets in all directions. This circular structure demonstrates that the rainbow's shape is determined by geometry rather than landscape. The familiar arc shape is simply the upper portion of a symmetric cone of refracted and reflected sunlight. When the environmental obstruction is removed, the symmetry becomes apparent, revealing that the rainbow has always been a complete circle of dispersed light, shaped by precise optical angles and the observer's position in three-dimensional space. In the end, a rainbow is far more than a beautiful curve painted across the sky. It is geometry in motion, physics made visible, light performing a silent calculation through billions of suspended droplets. It teaches us that what appears simple often hides astonishing precision. It reminds us that perspective shapes reality, that the rainbow you see is uniquely yours, formed by your position, your angle, your moment in time. The colours are not random, the angles are not accidental, and the arc is not incomplete. Everything about it is governed by the elegant laws of refraction, reflection, and dispersion working together in perfect harmony. When we truly understand a rainbow, we don't just learn about light. We learn about observation, about viewpoint, about how the universe responds differently depending on where we stand. The sky becomes a classroom, and curiosity becomes the real teacher. Science stops being memorized facts and becomes a way of seeing. So the next time you witness that spectrum after the rain, don't just admire it. Think about the hidden mathematics, the invisible symmetry, and the precision that makes beauty possible. Let it remind you that the universe is deeper than it looks, and that asking better questions reveals better wonders.